Picture this. You're hopping into a taxi, right? You know there's a starting base fare the second you sit down, and then a set charge for every single kilometer you travel. If I asked you right now to calculate the exact cost of a 15-kilometer ride in your head, how quickly could you actually do it? Well, what if I told you that by understanding just one fundamental math concept, you could predict not only that taxi fare, but the outcomes of literally countless everyday situations with absolute precision? Welcome to today's Explainer. We're diving straight into Chapter 2 of our core material to do something really cool, taking the somewhat abstract language of algebra and translating it into tangible, visual patterns that you can actually see and use. We are officially demystifying linear polynomials. So whether you're just looking to brush up on some rusty math skills, or you're a focused learner who wants a direct visual grasp of how numbers shape our everyday world, you are definitely in the right place. Let's get into it. Okay, let's take a quick look at our roadmap for today. We've got 6 steps. We'll start by decoding algebraic expressions, then build the input-output machine, move on to spotting linear patterns, contrast growth versus decay, transition to visualizing lines on graphs, and wrap it all up by decoding y equals ax plus b. First up, Section 1, decoding algebraic expressions. Imagine a scenario where a guy named Raju is buying sealed boxes of stationery. The red boxes have 4 pens each, and the blue boxes have 5 pencils each. Now, if Raju buys an unknown number of red boxes, let's just call that x, and an unknown number of blue boxes, let's call that y, and the store throws in 3 extra pens for free, how on earth do we write that out? Well, we get the expression you see right here, 4x plus 5y plus 3. It's like a giant puzzle, but we have all the pieces. Here, x and y are our variables. They stand in for the unknown quantities of boxes. The numbers 4 and 5, those are the coefficients. They're telling us exactly how many items are packed in each box. And that number 3 hanging out at the end, that's our constant. It never changes no matter how many boxes Raju decides to buy. Now, what happens if we simplify things a bit? If we restrict our expression to a single variable, say we just focus on x, and we make sure its highest power is just 1, we get what mathematicians formally call a univariate polynomial of degree 1. Kind of a mouthful, right? But honestly, we commonly know it by a much friendlier name, a linear polynomial. This right here is the foundational star of today's explainer. Think of expressions like 2x plus 3 or 4x minus 1. They're simple, they're direct, and as you'll see, they are incredibly powerful. Moving right along to Section 2, the input-output machine. Try thinking about a polynomial like 2x plus 3, not just as boring letters and numbers on a page, but as a physical, working machine. Seriously, picture it. If we drop an input value into the top of this machine, say x equals 4, the machine gets to work. It multiplies that 4 by 2 to get 8, adds 3, and then spits out an output of y equals 11. It's a continuous, totally predictable process. Feed it an x, get a y. It transforms known inputs into predictable outputs, making it this brilliantly functional model of reality. That brings us to Section 3, spotting linear patterns. Let's loop back to our taxicab from the very beginning. Here, the total cost, c, depends entirely on the distance d. The formula we're working with is 100 plus 60d. That 100 is our base fare constant, just for getting in the car, and the 60 is our coefficient, which is the rate per kilometer. Now, look really closely at the output costs. We go from 100 to 160 to 220 to 280. Do you spot the pattern? For every single kilometer we add to our input, the output cost jumps by exactly 60 rupees. No surprises? This constant difference between successive values, that is the absolutely defining characteristic of a linear pattern. Which leads perfectly into Section 4, growth versus decay. Let's stick with our taxi fare for a second, because we are continuously adding a constant amount of 60 rupees over equal intervals of kilometers. The numbers march steadily upward. We call this linear growth. But now contrast that with a totally different real-world scenario. Imagine a water tank that starts out with 3 meters of water, but it loses 0.5 meters every single month because people are using it. The formula there is 3 minus 0.5t. So month 1, it drops to 2.5 meters. Month 2, down to 2.0 meters. Because we are subtracting a constant amount over equal intervals, this is known as linear decay. The cool thing is both of these are perfectly linear. They're just heading in opposite directions. All right, Section 5, visualizing lines on graphs.
To see how this builds our visual understanding, let's grab an equation like y equals 2x plus 1. To actually see its true shape, we literally only need two input-output points. That's it. If x is 0, y is 1. Boom, there's our first coordinate pair, 0, 1. If x is 3, y is 7. That's our second pair, 3, 7. Now, when we plot these coordinates onto a Cartesian plane and connect them with a ruler, they magically form a perfectly straight line. And the really incredible thing, absolutely any point you pick along that infinitely stretching line is guaranteed to perfectly satisfy the original equation. It's a perfect visual translation of the math.
And finally, section 6, decoding y equals ax plus b.
So the absolutely crucial point to take away is this. Every linear relationship out there can be expressed in the universal format y equals ax plus b. This tiny, simple equation basically holds the DNA of the entire graph. The variable a is what we call the slope. It's the boss. It dictates the steepness and the direction of the line. The variable b is the y-intercept. Think of it as our starting block. It tells us exactly where the line crosses the vertical y-axis. And just like we saw with the taxi and the water tank, if a is positive, our line angles upward, meaning growth. If a is negative, it angles downward, meaning decay. Now, imagine tinkering under the hood of these parameters. If we keep our slope a identical at 2, but we change our starting point b from 1 to 5, we don't actually change the angle of the line at all. We literally just shift the entire line straight up the y-axis. We create perfectly parallel lines. Now watch what happens if we do the opposite. Let's keep our starting point at 0, but change our slope a from a positive 3 to a negative 3. The steepness is exactly the same, but the line completely reverses direction. It flips instantly from rapid linear growth to rapid linear decay. It's basically like having a steering wheel and an accelerator for a mathematical line, a total game changer. Wow, okay, we have covered some absolutely fantastic ground in this explainer. We've taken the abstract, squiggly symbols of algebra, built them into fully functional input-output machines, and painted their patterns as perfectly straight lines across a graph. The truth is, our world is totally full of these constant rates and starting points, everything from your mobile phone data plan to the speed of your morning train. So I'll leave you with this final thought. Now that you know exactly how to decode the math, what hidden linear pattern will you predict in your own life today? Keep your eyes open, folks. You are going to start seeing the algebra absolutely everywhere.